Hello, welcome to the Swansea University Department of Chemistry Analyst Contest. This is an online contest designed to temporarily replace what we would normally do when there's not a global pandemic going on, and that is to invite teams of 3 year 12 students to come to our lab and do 2 analytical chemistry experiments. Doing it online this year, I've got 2 experiments for you. You can do one, you can do both, whichever your teachers or you want to do. Everybody who successfully completes it and sends their data, their results to me, will end up with a certificate of attainment that will either be bronze, silver or gold, and those certificates are things that you can use on your UCAS application, which for many of you you'll be thinking about in 6, 7, 8 months. Anyway, the 2 experiments, this one here, we're going to talk about redox titration, and then a different one that if you want to, you can ask your teacher for, and that is a harder one on the analysis using spectroscopy of aspirin. Anyway, back to the redox titration. What you're going to do in this, and when I say you're going to do, I mean virtually, is you're going to investigate this compound known as Mohr's salt, otherwise known as ammonium iron 2 sulfate, and here's the formula here. It's known as a double salt because there's 2 different types of cations. You have ammonium and you have iron 2, and you have 1 type of anion, sulfate. You also have, as is common for quite a lot of ionic compounds in the solid state, some waters of hydration, waters of crystallization, whatever you want to call it. And the idea of this is to determine the value of X. Now, I should warn you that if you go look up Mohr's salt on the web, you'll find a certain value of X that I won't tell you because I don't really want you looking it up. But so that it's a little bit harder for you, I have partially changed this value of X. Okay, so X in this experiment is not going to be the value you could look up. It's going to be a different value. Anyway, the way you're going to do this is you're going to use a redox titration to determine how many ions, it's always tough to say, isn't it? Often I'll say iron ions, just to distinguish between them, in the salt, and then you're going to do some standard stoichiometric calculations to determine the value of X. Quick bit of chemistry background first. We're doing a redox reaction, so that means there's a reduction and an oxidation. The oxidation one is nice and easy. Iron 2 ions can be oxidized to iron 3 ions, so there's Fe2+, loses an electron, so it's oxidized to make Fe3+. Okay, so that is the oxidation. The reduction is what I call permanganate, you call manganate 7, MnO4-. No matter what you call it, it really is an excellent oxidizing agent. In other words, it's going to make something else be oxidized, make something else lose electrons, because the manganese in manganate 7 or permanganate is +7. +7 is a really positive oxidation number, and so the manganese atom would love to reduce that number, so wants to gain some electrons, and of course in gaining electrons it is reduced. Okay, so anytime you see MnO4- or KMnO4-, the first word to go through your head should be oxidizing agent. That's actually 2 words. It's a super oxidizing agent. Now I believe you're supposed to know one of the equations associated with that reduction of permanganate, and that is in acidic conditions in which the manganate 7, the permanganate ions, get reduced to manganese 2+ ions, and that is a very distinctive color change. Permanganate is a deep purple once it gets reduced to the Mn2+. The Mn2+ we think of as being colorless. If you look at it with a really good spectrometer, you can see a certain amount of pink electronically, but essentially you say purple to colorless in acidic solution when permanganate is reduced, in other words when it acts as an oxidizing agent. So we're going to take something that really wants to be reduced with something that is quite happy to be oxidized. and we get this overall equation. Do notice the balancing, because you'll have to use this very, very significantly later on. Each manganese needs 5 electrons to go from manganese 7 to manganese 2. Each iron needs 1 electron to lose 1 electron to go from iron 2 plus to iron 3 plus. So it's a 5 to 1 stoichiometry that you'll need to use. Okay, and as I said, we'll watch the reaction from the color change from purple to colorless. Really something to memorize there, to remember there. When permanganate acts as an oxidizing agent, when it's reduced in acidic solution, gains 5 electrons to go to Mn2 plus, purple down to colorless. Now in this particular experiment, it's going to seem like a twist, because we're going to start off with a whole bunch of iron in solution from our Mohr's salt. So we add a little bit of permanganate, it's purple in the burette, but when we add a little bit of it, it will go colorless because it gets used up by the iron. Then we add a little bit more permanganate, it goes colorless because it gets used up by the iron. And only when the iron is all used up does the solution stay a little bit pink, not fully purple, but pink, because we just added a little bit of unreacted permanganate. So a little bit of excess permanganate means that the solution stays pink, and you'll see pictures of this as we go through. So let's go ahead and do the experiment itself. Obviously, I did the experiment for you, taking pictures and videos. First part, preparation of the solution of the Mohr's salt. So we're going to take some of the ammonium iron 2 plus sulfate XH2O, and we're going to dissolve it up in an appropriate solution. Okay, so the first step is we need to weigh out some of that Mohr's salt. It's a solid, and we need to record the mass that we're going to be used. Okay, very important that we know as precisely and as accurately as possible how much of this Mohr's salt we're going to start with. So here is my balance on which I have put a weighing boat, and you can see that weighs 0.9657 grams. Then I'm going to add some of the Mohr's salt to it. And experimental technique point, you always add what you're weighing in the weighing boat outside of the balance and then put it back on, because if I was to just take this and start spatulaing out some of my solid here, some of it might get spilled, it would mess up the measurement, it would make the balance yucky, and so on. So anyway, I took this weighing boat outside the balance, I added some of this lovely sort of a pale turquoise almost Mohr's salt solution to it, and then reweighed it, and now it's 5.0344 grams. So your first little calculation will be how much actually did I weigh out of my Mohr's salt. And I took that, put it into a conical flask, added 50 cubic centimeters of sulfuric acid, because remember we need to be in acidic conditions, stopped it and shook it for 5 minutes. I timed that, don't really see why we had to time it, to dissolve the salt, and just to prove that I did. There is the picture of the conical flask with the stopper in it, and hopefully you can see there's no solid left in there undissolved. So, having dissolved it up, I now transfer the solution to a 100 cubic centimeter volumetric flask. This is what a volumetric flask looks like. It's got a sort of bulbous bottom, although the actual bottom itself is flat. And then it has this skinnier neck going up there, and there's the stopper. So I put my solution in there, added that more sulfuric acid to make it up to the 100 cubic centimeter mark. This was a 100 cubic centimeter volumetric flask, and when I added it up to that mark, you can see it right there. There's the meniscus of the solution right at the mark itself. So that was part one of the method, nice and easy, making up a 100 cubic centimeter solution that contained all that Mohr's salt that we weighed out in a previous slide. Part two, we're going to do the titration now. We're titrating it with a solution of potassium permanganate. So rinse a burette with a small volume, 0.02 moles per cubic centimeter, potassium manganate 7 solution, that's the permanganate, and then fill the burette with that same solution. Now again, little bit of experimental technique to discuss here. Okay, a burette is this long glass cylinder here. Okay, and when you have a fairly high bench like we do in our lab, and I'm sure some of you do, the top of the burette can be sort of 7 feet above the top of floor level. When you fill a burette, you need to put a funnel in there. But then if you're not tall enough to be able to reach and pour into that funnel, so that, as you will see in a minute, the funnel is below your eyes, you need to lower it until it is. And a lot of times that will involve actually the burette sticking off the edge of the bench. So here you can see my burette sticking off the edge of the bench, and then a very embarrassing picture coming up. Now I can see the top of the funnel when I do it. That is me, not Santa Claus or anything silly like that. And now I can fill it up using my nice purple permanganate solution, or manganate 7 solution, again using the funnel there. Now you can't see it beautifully here, but this is actually above the 0 mark. Okay, so anyway, one sentence, but does require some significant experimental considerations. Next step, we're going to use a 25 cubic centimeters pipette and a pipette filler provided, measure out 25 cubic centimeter sample of the Mohr's solution into a clean 250 cubic centimeter conical flask. So here again, going to my general picture, this is a 25 cubic centimeter pipette that has a pipette filler on the top of it. If I look more closely at my pipette filler, there's the 25 cubic centimeters. And then an important little note that you'll see on a lot of precise glassware is how precise is the glassware itself. Well, and we'll come back to this later on, the pipette is plus or minus 0.1 cubic centimeters. So anyway, I use this to suck up enough of my Mohr's solution, and there it is there. You can see the meniscus just touching the very, very right mark at the top of the pipette. So next step, using 25 cubic centimeter measuring cylinder, measure out 25 mils of Mohr acid in there. Fast question I would have had for you if you had been here in person. Why am I using a measuring cylinder for an acid? A measuring cylinder is precise to within plus or minus 1 cubic centimeter, whereas for the Mohr's salt I use the graduated pipette, much more precise to within 0.1 cubic centimeters. What's the difference? Well, the difference is that the sulfuric acid is just there to make it an acidic environment. 24, 26 cubic centimeters, who really cares? On the other hand, the Mohr's salt solution contained one of the important reactants in the reaction, the Fe2+. If I'm going to do any kind of calculations, I need to know as precisely as possible how much of the reactants I'm using. Anyway, now we're going to go ahead and titrate this by adding potassium manganate 7 from the burette till the first permanent pink color is seen after swirling. So here is my burette. I'm starting at 0. You don't have to start at 0. You can start wherever you want as long as you record it and it's easy to read. And quickly point out, burettes are even more precise than the graduated pipette that I used. This burette is plus or minus 0.05 cubic centimeters. So anyway, here's the setup. I'm going to apologize for my technological ignorance here. This is a picture I took on my iPhone. It looked really good like this, except it's on the side. There is my 250 cubic centimeter conical flask. It contains the 25 mils of the Mohr's solution, nice and precisely measured, another 25 mils of the acid. There is my burette with the tip pointed at it. Now I'm going to press play here just so you can see what's happening, and because it will be clattering around just to provide realism of the stirrer bar, I'm going to say I'm just going to add a little bit of the permanganate to the solution. The color will very, very quickly disappear as the permanganate reacts with the Fe2+, and I'm going to show you a couple of those type of additions. So there we are. There I am adding it. Excuse the squished nature, like I said, technologically ignorant. Add it in. You can see the color very quickly disappears because the Fe2+ reacting quickly with it. Now, as I get close to the end of the titration here, and you can see it's still nice and colorless in there, okay, but now I've added, I think at this point I'd added about 24.5 cubic centimeters of the permanganate. So again, let me give you the squished up view of the whole thing. What I want you to see here is, first of all, the first little addition of the permanganate, and the color goes away, but it doesn't go away as quickly. And then the second, it doesn't go away as quickly. add it. See, it persists a little while. Add a bit more, persists a little bit more, add a bit more, and now it stays pink. And the reason why it's staying pink there is because I've used up all the Fe2+. So in other words, I've reached the equivalence point of the titration, and now you can see the end point because that last little drop of the potassium permanganate that I added didn't react, and so it stays purple, except of course it's so diluted, the diluted purple is pink. Okay, so that pink color is unreacted potassium permanganate because I'd used up all the Fe2+. How much potassium permanganate did I have to add? Well, here is a nice big picture of what the burette looks like. Remember, we started at 0. And I've added enough now, 25.1, 2, 3, 4, that's 25.5, 25.6, 25.7. And I'm going to say, as you will see in a minute, that because I can read it to within plus or minus 0.05, I'm going to say that that's 25.75. Okay? Anyway, here are the results with the solid. If you remember earlier, I showed you the mass of the Wayne boat. What was that? And then the mass of the Wayne boat plus the Mohr's salt. So that will give you the mass of Mohr's salt that I added in there. For my titration, the KMnO4 solution was 0.0200 moles per cubic decimeter. So that's good within 3 significant figures. And then my rough titration here, I took 25 cubic centimeters of the Mohr's salt solution. Starting burette was 0, as you saw, ending burette 25.75 cubic centimeters. Then I did it a little bit more precisely, again 25 cubic centimeters. Here, burette started at 5, just because I couldn't reach all the way up to 0, and I added enough to get up to 30.5, and then my second accurate or precise one went from 0 to 25.8 cubic centimeters. I personally spend a little bit more time on my rough measurement, so I might, if I wanted to, use those data. Otherwise, just use data points 1 and 2. So we talked about the experiment. We did the experiment in quotes. You got the results. Now you can do the calculations to determine exactly what is the value of X in my sample of Mohr's salt, which, as I mentioned at the start, may or may not be an unadulterated version of Mohr's salt. Anyway, there are 7 questions here. If you want to get one of those certificates, you upload the answers to this online answer sheet. It's a live link here, so if your teachers give you the PowerPoint that comes with this movie, you just have to click on that and enter your answers. Failing that, then in the email I send to your teachers, I will include that link in there. So anyway, 7 questions. First one. What is the average volume of KMnO4 solution added to the 25.0 cubic centimeters of Mohr's salt solution? Each titration I started with as precisely as possible, 25 cubic centimeters of the Mohr's salt. I added the potassium permanganate. You can either use all 3 of my titrations, because my rough one was actually a pretty good rough one, or you can just use the 2 accurate ones, accurate being in quotes there. Once you've got the volume, knowing that the concentration of the potassium permanganate solution was 0.0200, you can get the number of moles of potassium permanganate. You can then use the equation that is right at the start. How many moles of Fe2+ will react with this many moles of KMnO4? Now, how many moles of Mohr's salt does this correspond to? That's a very easy question because there's 1 Fe2+ in each Mohr's salt. Now, using my answer to 4 and the mass of Mohr's salt measured in that step 1, that's on the balance, and not falling into a little trap here, what's the molar mass of Mohr's salt? This will be the calculation on which you're most likely to fall down. So you got the molar mass of Mohr's salt. That includes, when you weighed it out, all the waters. So now you can calculate the value of X. And then as a final little one, I told you the burette was precise to plus or minus 0.05 cubic centimeters, and the pipette was precise to plus or minus 0.1 cubic centimeter. What are the upper and lower bounds of the answers to questions 1 and 2, knowing the precision of the two bits of equipment that you used to measure things out? Anyway, hope this was fun. Hope to see lots and lots of entries through my online answer sheet. And any questions for this, ask your teachers and they will pass it on to me if they want to. So anyway, and I hope that as we get through the pandemic, that your teachers will bring you to our labs to do some actual real live experiments. Goodbye.